On that note, good afternoon. So on last Thursday, we started by talking about something that you should be very familiar with, namely the ethylene double bond. And we discussed hybridization and the fact that we have two p orbitals overlapping and that the electrons are delocalized. And then we asked the question, what happens when you add another carbon to this chain that is also sp2 hybridized that has another p orbital, namely an arrangement like this? And we established that these guys, since they're all equivalent, they start overlapping with each other. And we got what we call the allyl system, or the 2-propenyl system. And depending on whether it's a radical, that is some electron, a single electron in a resonance form that puts it at one end, you can delocalize that radical over the pi system. If it's a charge, it's a delocalized cation. If it's an anion, if it's a positive charge, it's a delocalized cation. If it's a negative charge, it's a delocalized anion. Let's say cation and anion. So in the radical case, we went a little further and talked about an unsymmetrical scenario where instead of having the symmetrical allyl system where it doesn't matter where the bromine attacks to make the corresponding allylic bromide, because both ends are the same, once you put a substituent at one end, it's unsymmetrical, the two ends are now different, and you get product mixtures. And so building on that, I wanted to start with a problem on the board that would be a typical midterm problem. Okay? So of the type that you'll see in the midterm, you may even see this one or a variant thereof. There's only so many things you can do with a particular theme. And that is this compound here when treated with NBS. Remember, NBS is N-bromosuccin imide. You can, if that's too much of a mouthful, if you just use the term NBS, that's fine, on top of an arrow. It's a source of slow delivery dilute bromine, and it's the bromine that does all the stuff, namely it dissociates and you get bromine dot, and then you start a radical halogenation cycle that goes through the two propagation steps that we wrote. And so the question is, what are the products? And the second question relates to optical activity, because as you can see here, and this would be stated in the exam question, it's only this enantiomer that I want you to react. So it's an optically active enantiomer. And to start off this, the answer to this, we need to, I'm asking you to name it. That serves as a review of alkene nomenclature, chapter 11, as well as RNS nomenclature, namely enantiomer names. That's from chapter 5. So let's first find a name for this, and when you look at the, hang on. So in answering any questions, what you might find useful, and I don't know to what extent you did it in Chem 3A, is to use what we call the WIP approach. Okay? Some of you may think that this is ridiculous, so then don't use it. But if you just think of the term WIP, it organizes your thoughts, and it guides you into a stepwise approach to the solution, rather than, in a panic, starting to delve into the problem, trying to solve it, and going up the proverbial shit creek, namely you just go on the wrong tangent and you never come back and lose a lot of time and so forth. So what does WIP stand for? The W is for what, meaning first back off and look at what you have. Okay? What is the starting material? What's on top of the arrow? What does the question ask? The H stands for how, meaning how would you approach this? What is necessary to approach the solution to the problem? In this case, clearly what is necessary is a mechanistic understanding of what clearly looks like an allylic halogenation. Okay? And then the I stands for information needed. So if you're working at home, you just check the chapters if you can't remember. Otherwise, you check your memory banks and you come up with information which is related to for naming, to the rule for RS nomenclature and so forth for this problem here, the CH bond strength. Okay? And then the P stands for proceed. Okay? Then you can get started. Okay? That gives you at least some organized way of approaching the problem. So naming this is clearly a cyclohexene, and it's got a methyl group, so it's a methyl cyclohexene. And so now we have to specify where the double bond is and where the methyl group sits. And so that means numbering the ring. And the priority group is the functional group, which is the double bond. So we can start here, 1, 2, 3. That would be one way of starting naming numbering the double bond. Or we can start here, 1, 2, 3, 4, 5, 6. So out of these two choices, as you know, we always pick the one that gives the lowest numbered locant to the first substituent. So we start here, 1, 2, that gives the methyl a 3 rather than a 6. Okay? So it's a 3-methyl cyclohexene. And the next problem is to identify whether this is ROS. So everybody has it. So this goes back to chapter 5. How do we establish the three-dimensional arrangement of the four substituents around a stereocenter? And you may remember, hopefully you do remember, that we organize all the substituents in order of priority using the priority rules, the Kahn-Ingold-Predok priority rules. Namely, we number them A, B, C, D from highest order to lowest order, highest priority to lowest priority. So if you look at all this, hydrogen is clearly lowest priority, so this has got a D. The other four atoms substituting the center are all carbons, but this carbon is a double bonded carbon, so this is clearly higher priority. This is secondary, and this is a metal. So this is B, and this is C. And once you've arranged that, then you can use, again, a number of tricks, and that's very personal. It depends on how good you are in, looking at things in 3 dimensions and doing calisthenics and acrobatics and dancing around the molecule. Okay? I like the dancing around the molecule or sitting on the molecule, so I basically approach this carbon and in such a way that I look down the bond that leads to D, the lowest priority substituent. Because once you have that, if I sit there, the carbon is here and the lowest priority substituent is there, what is pointing at me is the remaining 3 substituents, and they're either arranged counterclockwise, S, or clockwise. Okay? So in this particular case, I look down, I'm sitting. Well, I look down this way, so imagine, of course, that even though we're off, the bonds are sort of off straight, in reality, the molecule is slightly offset. In reality, of course, this guy is coming out towards you, and this guy's going to the back. Okay? So in order to depict this better, we sort of slightly rotate the molecule to make the wedge go in one direction and the dash in the other direction. But really, this is behind the blackboard. This is in front. So if I look down this way, the H is behind the board, and that means that on top right is A, and top left is B, and at the bottom is C, the way I view it. And that means it's A, B, C, means it's S. So that's a little bit of nomenclature. So now let's look at the problem and see what happens. And so the issue really is a mechanistic one. We know that the crucial step in the crucial species attacking this guy is bromine dot. So bromine dot is the protagonist that will look at this menu, okay? And it has a whole bunch of hydrogens at its disposal. In principle, it could plug off any one of them to make HBr, right? And so what does it choose? That goes back to chapter 3, radical halogenation of branched hydrocarbons. And there we learned it goes after the weakest bond. We already repeated that last Thursday. The weakest bond is the allylic bond. So it's either this or that position. So we here have, since it's unsymmetrical, we have two allylic bonds. So which one is it going to choose? Again, it's the weakest CH bond. So when you compare this bond, which is a secondary, versus this hydrogen here, which is tertiary, we know tertiary CH bonds are weaker than secondary CH bonds by 2 or 3 kcals per mole. Okay? So bromine will attack here. And that is, gives away really the answer. So it's very quick once you know what you're doing here in terms of mechanisms. We have this radical. What we have to write is that the fact that it's a delocalized radical that looks like that. But the key point to notice is that as soon as you plug off this hydrogen from the stereocenter, that stereocenter is killed. Okay? The stereochemistry is lost. And the products that you get are flat. They're achiral. Which means that any product that comes out of this achiral intermediate will be racemic, not optically active. And it may be achiral or not, that's irrelevant. The fact is, you can't generate a chiral and optically active compound from an achiral system. The optical rotation is lost. Once it's lost, it doesn't come back. Okay? So everything would be racemic. So looking at these two guys here, the products that you should get are racemic bromide at the tertiary position plus racemic bromide at the secondary position. And notice, oops, I've written it like that. I'm using straight lines, meaning that the two can be inverted. I'm not indicating stereochemistry. This is a stereocenter. This is also a stereocenter. But when we draw a straight line, it means it's racemic. It's implicit. You could also write both enantiomers if you wanted to and say both enantiomers are formed in 1-to-1 ratio. And the reason for that is that this is flat, so attack from the top is equivalent to attacking from behind. It should be, because they're two different products, but we established last week that it's hard to predict. One could argue, if you were to ask a best guess, my best guess, and probably yours too, would be this is more sterically hindered, so you probably get less of that. But that's not absolutely clear. Because these are very active species, and it depends on dilution and a variety of factors. Yes?
What is the other radical not attacking
Here? Because this is secondary. Yeah. That's what I said. So both of these are allylic. So what's the difference? This one's tertiary, this is secondary. So the rules of chapter 3 still hold. Okay? So if everything is equal, there are several allylic hydrogens. You decide which CH bond is the weakest based on tertiary, secondary, primary methyl rules, right? So, but that was a good question because I wanted to give you a homework problem that addresses exactly that. Since the difference in CH bond strength between the two positions is only about 2 or 3 kcals, you will get a little bit of a side product, less than 1%, so therefore synthetically irrelevant, but mechanistically interesting, of attack at the top. And so my question is, what are the products? And are they optically active? And you can't do it now because it requires that you sit down and draw out all the possible compounds that you might form, establish whether there are isomers, and then establish whether they're stereoisomers, and then figure out mechanistically as you go to the mechanism, whether in the mechanism of plucking off a proton from hydrogen from here, you also go through an achiral intermediate, or in fact whether the stereochemistry at the stereocenter is preserved, in which case the chiral information is not lost, it stays there. Okay? And so everything else then falls into place relative to the already existing substituent. All right, so much for allylic radicals. But we also indicated already last Thursday that there are other indications of unusual stabilization of the allylic system in other types of reactions. And one of them is the SN1 process, namely, and this SN1 occurs relatively readily from allylic systems because the allylic cation is also stabilized. And we established that even primary substituents, leaving groups at primary carbons, will leave when they are allylic. And so if you let this thing sit around in a non-nucleophilic solvent, non-nucleophilic meaning that there is no strong nucleophile around that will do SN2, we'll come to SN2 in a second, it just sits there, and typically the solvolytic conditions that people use are water or alcohols. Sometimes other solvents that are non-nucleophilic, but those are the two major classes that we have learned anyway. And so in this case with water it would be hydrolysis. Water is not nucleophilic enough to directly attack this carbon to do an SN2. It just stares at it. Okay? And the halide has enough time to dissociate spontaneously every now and then and make the corresponding allylic cation. And of course we can write two resonance forms, okay? Where you put the positive charge at this end or you put it at this carbon here, and then you trap this with water. This goes initially of course through the protonated alcohol. I'm not even drawing this step anymore. It's completely analogous to the solvolysis of a tertiary halide. Where you go through a tertiary butyl cation, and then water attacks, you get the protonated alcohol, then the proton falls off. And so I'm letting the proton fall off all in this step. An attack can occur either at this carbon that gives you this alcohol, or at this carbon that gives you this alcohol. So two products are formed. And part of the ensuing discussion today will be what are the ratios. Here you can actually make predictions. And what happens to these alcohols, because notice we have an allylic alcohol here and an allylic alcohol here. Under the conditions we're forming H+, an allylic alcohol, just like a secondary or tertiary alcohol in the presence of H+, will get protonated again, and every now and then the protonated OH, which is water, will leave. And so this is reversible. Okay? So there can be an equilibration of all the products if you wait long enough. One thing that I wanted to emphasize, hopefully this was pointed out in 3a, free H plus doesn't exist, it's always solvated. So, but we write it as H plus, and we've entered in the new edition and the side and the margin reminder, H plus does not exist. In this scheme, it's most likely solvated by. In this case, it's most likely H3O plus. It's solvated by water. In other cases, it could be anything that has an electron pair. Okay? But since this is really very confusing to write what happens to the H plus and what way it is solvated, we just write it as H plus, okay, for simplification. And I think that's perfectly reasonable. Okay, two products. Now let's go to SN2 conditions. SN2 conditions is when we have a good nucleophile in solution that will attack the haloalkane before it dissociates. So this is very reminiscent of the chameleonic type or schizophrenic type behavior of a secondary haloalkane. Remember, under solvolytic conditions, no good nucleophile around, it dissociates SN1. If you have a good nucleophile, like iodide, you get SN2. Okay, so for secondary systems, both can happen depending on the nature of the nucleophilic species. So if the nucleophile is good, we get displacement. And this is direct attack on this carbon. Direct displacement with a good nucleophile is way faster than the SN1. SN1 is relatively slow. So another mechanism takes over, SN2, attack from the backside, remember, and we draw a transition state where the nucleophile, here I've drawn it such that the nucleophile comes in from underneath, and this carbon rehybridizes in a sort of umbrella-like motion, and the leaving group leaves. And this is a transition state, not an intermediate, not a species that can be isolated, it's just the maximum in our potential energy diagram. This is accelerated relative to the same compound without the double bond. So here it is, chlorobutane. This is 1-chloro-2-butene, and this is chlorobutane. In fact, this guy is about 100 times as reactive in SN2 as the other one. Yeah. Yeah, they're unhybridized. Takes too much, and they don't need to hybridize. Okay. But they're also too large and diffuse for hybridization to be advantageous. See, part of hybridization, this is probably now no longer on your radar screen, but is due to electron repulsion. Okay. You want to arrange, that's why we have trigonal, tetrahedral, linear, right? Because in these arrangements, you have all the electrons as far away from each other as possible. Okay. So that's rule 1, golden rule 1, Coulomb's law. Okay. Once the orbitals get larger, that is no longer such a big issue because they're already spread out in space rather well. Okay. This is sort of a simple and readily understood realization. But it doesn't really, even if you were hybridized, I don't know where you want to go with that because it doesn't really do much for you, right? Yeah. But no, they're not. So 100 times faster, and there are two reasons for this. One is that this carbon is more electrophilic than this carbon. Why is that? Well, notice the difference between that and that. They're both CH2Cl, but the next carbon is different. This one is sp3 hybridized, that carbon is sp2 hybridized. And switching, going from sp3 to sp2 means that you go from 25% S character, sp3 for orbitals, right? So it's only one S, 25%, to a third, 33% S character in sp2. That means that the orbitals that you use have more S character. The pure S orbital is a ball, okay? And the electron density, or the electrons in the S orbital, are relatively close to the nucleus compared to the p orbital, which is this figure 8 construct, where the electrons can be, on average, much further away from the nucleus. Okay? So more S character means that you basically tighten up the electrons around that nucleus, meaning that bonds from that nucleus to another atom, i.e. this carbon to that carbon, become polarized in the sense that this carbon pulls, because the electron density relative to this carbon is closer to its nucleus. Closer to the nucleus means the nucleus pulls on the electrons. Pulling on the electrons means you are making the neighboring carbon slightly less electron rich or electron deficient. Always relative to the case where this isn't there, right? And so that makes this more delta plus than that. So this is purely Coulomb's law, electrostatic effect. The nucleophile recognizes this is a harder carbon than this one. The second reason is the transition state for the SN2. Without the double bond, it would just be this. Okay? Nucleophile comes in, it attacks on the backside. H and Cl, there is an umbrella-type motion of the two carbons, the carbon and the two hydrogens, and the chlorine leaves on the other side. Okay? This umbrella-type motion means that in the transition state, this carbon goes through a three-dimensional array that is sp2 hybridized. So this carbon is like an sp2 hybridized carbon. It's a weird one because this orbital, this p orbital, is partly used for bonding on top to the chlorine that's leaving, and partly used for binding to the iodine at the bottom that's incoming. Okay? But it's just a smooth billiard shot type movement. The ball comes in the back, this kicks out the other end. Okay? And in this fleeting moment, which is the highest energy moment, this is sp2 hybridized. Now this sp2 hybridized carbon benefits, again, by allylic resonance from the presence of the neighboring double bond, meaning that relative to the transition state that you can draw for this guy, this one is slightly lower in energy, more favorable, more easily reached, okay? And the reaction is a little faster. 100 times is not big, but clearly in a synthetic scheme, if you get products in a ratio of 100 to 1, a synthetic chemist says this is quantitative. Great, because normally you get more like 5, even in a good reaction, 5, 10% of some side product. Right? So this is significant. We can also make allylically stabilized anions. And remember, we noticed that the allylic CH bond is unusually acidic. The pKa change was more than 10 pK units to lower numbers, meaning this is relatively acidic relative to the completely saturated system. And so this means that we can pull off this proton, just like we can pull off a proton from a normal acid.